Well, hello and welcome again to Math 315, and this is the fourth video for chapter 2. And here we're going to introduce the monotone convergence theorem, which is one of our very most powerful tools that we'll see in dealing with more complicated sequences where we can't use our common sense. These are particularly useful in dealing with recursively defined sequences, and we've mentioned these before. Now we're going to do something with them. So to deal with recursively defined sequences and many other things, we introduce the following extremely important theorem. We firstly say that a sequence AN is monotonic increasing if each term is bigger than the term before it. Well, perhaps eventually, for all sufficiently large n. In other words, if we look at a picture of this, we can see we're looking at a sequence like this where the terms just continue to get bigger and bigger. They never go back or lower. Each term is always bigger than the term before it. And I'm going to state without proof the following very important theorem called the monotone convergence theorem. If AN is a monotonic increasing sequence, AN, and there's a brick wall up here somewhere, so the sequence is getting bigger and bigger and bigger, but it's bounded above. There's a brick wall here at K. Then the theorem says that this AN converges to something. It might converge to K, but in general it's going to converge to some other number L that's less or equal to K. So if the sequence is increasing, there's a brick wall up here somewhere that it can't get past, then the sequence must have a limit L which is less or equal to capital K. Now I'm not going to go through the proof here since it requires some ideas that we haven't looked at yet. Indeed, it requires some ideas involving the fundamental properties of the real numbers, in fact, and so we're not going to do that here. While the idea in the above theorem is sort of obvious, if it's continually increasing and it can't get past somewhere, then it's going to have to settle down to some limit L. It actually relies on fundamental ideas about the nature of the real numbers themselves, and you can replace monotonic increasing and bounded above in the theorem by monotonic decreasing and bounded below. That is, if the sequence is coming down this way, and there's a brick wall at the bottom it can't get past, then it will have a limit as well. And so we'll be using both forms of this theorem. Very simple example of a monotonic of one of these is the following. Here's a very simple example of this. Is the sequence AN is 1 minus 1 over n. It's clearly monotonic increasing. So the first term would be 0, the second term will be a half, the next term will be 2/3. The terms are getting bigger and bigger and bigger, and it can't be any bigger than 1 because it's 1 minus something, so it's bounded above by 1. And hence, the sequence converges by the MCT, monotone convergence theorem. I'll use MCT as an abbreviation. It's obvious that the limit, in fact, is equal to the number 1. So that's no big surprise. I'm going to do a number of examples of this one. Firstly, a slightly more complicated example here, but just to show you the power of this. So I define the following sequence. I take the first term, I take the sine of 1 on my calculator in radians, so I get some decimal. I then take the sine of 1 and the sine of 2, and I take whichever is bigger. I then take the sine of 1, the sine of 2, the sine of 3, and I take whichever is bigger. And so I'm going to get a sequence of numbers here. They're not very nice decimals. You might like to actually evaluate these yourself and see what numbers you get. And the general one's going to be I take the sine of 1, 2, 3 all the way up to sine n, and I take the maximum. Now it's pretty obvious that this is a monotonic increasing sequence because I'm adding more stuff in and I'm taking maximum all the time. So it's going to be getting bigger and bigger and bigger. It may stay the same at some point, but it's not. It's either staying the same or it's getting bigger as we move along. and it's clearly bounded above by 1 because the sign of anything can't be bigger than 1. And so by the monotone convergence theorem, it has some limit which is less than 1. Well, in fact, turns out it can't equal 1, but we might say less or equal to 1, but in fact it happens to be strictly less than 1. Now, it's not clear at all what this limit is. I can't tell you what the value of the limit is. It can't be easily found. So the theorem only guarantees that the limit exists. It doesn't tell us necessarily what it is, just that it has a limit, but what it is, that's a different question. Now, the following example shows how useful the theorem can be when dealing with recursively defined sequences. And this is an important example. We'll do some more of these in here, and we'll also do some more of these in the tutorials. So look carefully at this particular example. So here's our sequence. What you do is you start with A1 is 1, and then you square it and add 2 and divide by 2 times 1. So that would give you the next term. So A1 is 1, and then A2 would be 1 squared plus 1 is 3 over 2, which is 1.5. And let's just work out A3. So we're going to take this number, we're going to square it, plus 2 over 2 times 3 halves. So that gives me 9 quarters plus 2 over 3. 4 2s are 8, that's 17 over 8. So we're going to get this sequence. You take each term and then you square it, add 2, divided by twice that term, and it gives you the next term in the sequence. So you see it's quite a complicated sequence. Now we looked at this sequence earlier, in fact, and we proved before that it was bigger or equal to root 2. You may remember, I might just remind you how we did that. What we did last time, just to remind you how we did this, we said that an squared plus 2 over 2, we used and I'll take the 1 over an out, and so we used the AMGM inequality and said this is the average of these two. So that was bigger than the square root of their product. And when you simplified that, you saw we got root 2. So we did that before. We proved that this sequence is always bigger or equal to root 2. So that means it's bounded below. This one here, we also showed that an plus 1 is less than. And that means the sequence so it's bounded below, all the terms are less than root 2, so bigger than root 2 I should say, so all the terms are up here somewhere, and we're going to show that it's getting smaller. That means each term is less than the one before it, so as I move along the terms are now getting smaller. Remember, we did this one, just to remind you again, you might like to look back, we did this one by looking at an plus 1 minus an, and we showed that that was equal to 2 minus an squared, I think, over 2an when we simplified it. And because an is bigger than root 2, an squared is bigger than 2. And so this was negative, and that's the same as then saying that an is plus 1 is less than an. So that's what we did that before in a previous recording, just to remind you of what we did. So that tells me that the sequence is bounded below. There's a brick wall here at root 2, and it's monotonic decreasing. It's getting smaller. And so by the monotone convergence theorem, it has a limit as n goes to infinity. The theorem doesn't tell us what the limit is, it just says it's got one. However, what we can do is we can take this recursion here, and if the limit is alpha, then I can take limits in the recursive formula. That is, I can say that the limit as n goes to infinity of a sub n plus 1 is the limit as n goes to infinity a sub n squared plus 2 on 2a sub n. And as n goes to infinity, this is going towards a, and this is going towards a squared plus 2 over 2a. I think I've used alpha, in fact, rather than a. So I better put some alphas in. So we get alphas, and that's where this is coming from up here. So we have alpha then is alpha squared plus 2 on 2 alpha. I can cross multiply. I get 2 alpha squared is alpha squared plus 2. That gives me alpha squared is 2. And that means alpha is root 2. Can't be negative root 2 because the terms are all positive. So in fact, in this case, the brick wall was the point to which the sequence was converging, that is root 2. That won't always be the case in these problems, but that's what it is. Now you'll see another one similar to this one in the tutorial problems. Now I wanted to do a slightly more complicated one, but again, this is fairly fundamental that you'd be able to do this. There's one of these again in the tutorial problems, and we're going to be doing this by induction. So you may need to revise your induction. If you've forgotten how to do proof by induction, you may need to revise that one there. So here's our sequence. It says you start off with 2. So you get 2 plus 2 is 4 over 4 is 1, so the next term is 1. Then you put 2 plus 1 on 4, you get 3/4, and then you put 2 plus 3/4 on 4, and so on. So you might like to write out the first few terms of this for yourself. So this is giving me some kind of sequence. Every term in the sequence, to get the next term in the sequence, we take the previous term, add 2, and divide by 4. So here it is. There's our sequence. So A1 is 2. You put 2 in, you get A1 is 1. And that means at least then that A2 is less than A1. This one is less than this one. Now we're going to use induction. So with induction, you have to check the first case. The statement is true when in the first instance, and it is. We've just checked that here. Now, we're going to suppose that the inequality an plus 1 is less or equal to an is true for some integer k. So this is the inductive step, the inductive hypothesis in induction. That is, we're going to assume that ak plus 1 is less than ak for some particular integer k, and we want to show that the same is true if I bump it up, if replace k with k plus 1, the same result is true. And that's the inductive part of the proof. So now we consider a sub k plus 1. Now we use our formula here. So this says that this number, you take the previous number, you add 2 and divide by 4. So you take the previous term, add 2 and divide by 4. Now I use my inductive assumption, that is ak plus 1 is less or equal to ak. So I can replace this one, less or equal to ak. But hang on, now I've got 2 plus ak divided by 4, but that's just the next term in the series, in the sequence I should say. And that means I get a sub k plus 2 is less or equal to a sub k plus 1. And that means the result is true also for k plus 1. So if the result is true for k, then it's true for k plus 1, and it's true at the beginning, and hence it's true for all n bigger or equal to 1 by induction. I should say perhaps hence true here for all n bigger or equal to 1 by induction. I hope you've mastered your induction. It's in the high school syllabus, and it's an important skill we're going to be using a lot. Now, using part A then, I can say we were asked then to show that in the question we were asked to show that an is less than equal to 2 for all values. So it's got an upper bound in fact. So an is less than an minus 1, but then I can say that one's less than the one before it. all the way down to the beginning, and that was 2. So that that says an is less or equal to 2 for all n. Now our sequence up here, we've shown up here that the sequence is monotonic decreasing. That's what we just showed, and I need to get it bounded below by something. We've got it bounded above, but I want to get it, in fact, because it's decreasing, I want it bounded below. So the terms are all getting smaller, one after the other, and I want to get a brick wall at the bottom. Well, there's an obvious brick wall to take, and that is all the terms are positive, so I can just say that an is bigger or equal to 0. Okay, so the sequence is, it's a decreasing sequence like this, and I just want to get a brick wall somewhere. Well, the terms all have to be bigger or equal to 0 because they're all positive. So it's bounded below by 0. Hence, by the monotone convergence theorem, this one converges to some limit alpha, and that means I can then take limits through the recurrence again. So there's the recurrence. An plus 1 is 1/4 an brackets an plus 2. Take a limit of both sides. This one goes to alpha, this goes to 1/4, this goes to alpha plus 2, and now I can multiply by 4, and I can solve this very easily for alpha, so alpha is 2/3. So the limit of this sequence, in fact, is just 2/3. So notice here, even though our lower bound was 0, the actual limit, the real brick wall, is the thing it's headed towards is actually 2/3. Now there's another one of these to do in the tutorial problems, and we'll do another example in a second. So that's a nice example for you to work through carefully. Make sure you can follow that one. I want to do a quick example here now. This is an plus 1. Is equal to the square root of an plus 1. So you start off at 1, and what you do is you add 1, push the square root button on your calculator. Add 1, push the square root button on your calculator. Add 1, push the square root button on your calculator. So what you're going to get is then a sequence of numbers. You might like take your calculator and actually do that. 1 plus 1 is root 2. And so you take root 2 and you add 1, push the square root button, see what you get, and then add 1 to that, push the square root button, you'll see you'll get a sequence of numbers coming out. And we'd like to know exactly what the limit of that sequence is, and you're going to be, I think, quite surprised when you see the answer to this. So here is the full derivation of this using all of the tools, the monotone convergence theorem. So firstly, the first term is 1. The second term, put 1 in here, you get root 2, which is about 1.4. And if you keep going with this, you'll see each term you get, the terms appear to be increasing. So we've got a sequence of numbers that's getting bigger and bigger and bigger. Now, we have to prove that. We have to prove that result. So I claim that the sequence is increasing. That is, each term is bigger than the term before. And again, we're going to do this by induction. We're going to do this by induction. The statement is certainly true when n is 1 because this number here is bigger than this number here. So so A2 is bigger than A1. So the statement's true when n equals 1. Now we make our inductive hypothesis. We let k be an integer for which ak plus 1 is bigger or equal to ak. Then I have to show that we've got a similar inequality with k replaced with k plus 1. So I'm going to show it also works for k plus 1. So I look at ak plus 2, and I go back to the definition. Remember, the recurrence was to get any new number, you take the previous number, add 1, push the square root button. That was what the recurrence was. Now I use the fact that ak plus 1 is bigger or equal to ak, so I can put a bigger equal to sign and replace that with ak. And I use the recurrence again, because if you take any term plus 1, push the square root button, you'd get the next term in line, which is a sub k plus 1. Now look what we've written. We've got a sub k plus 1 is bigger or equal to plus 2 is bigger than a sub k plus 1. So that says the statement then is true for k plus 1, and so it's true for all n bigger or equal to 1 by induction. Hence the sequence is increasing. That's what we wanted, to show it's increasing. Now if you look at the first few terms, you get 1, 1.414. As I mentioned, you should play with your calculator with this. You'll see that all the terms appear to be less than 2. I could have put 3 here, I could have put 5 here, but I chose to put 2 because when I started calculating these numbers, they all look as though they're less than 2, so I just make a guess that there must be a brick wall at 2. They can't get any bigger than 2. And again, we're going to prove this by induction again. And we use lots of induction here. The first term is 1, which is clearly less or equal to 2, so the statement's true for n equals 1. We let k be an integer for which the kth term is less than 2, and I've got to then prove the k plus 1th term is less than 2. And again, so I look at a sub k plus 1, go back to the recurrence. This is the square root of the previous term plus 1. Now the a sub k is less than 2, so I can replace the a sub k with a 2. And 2 plus 1 gives me root 3. So if a sub k is less than 2, a sub k plus 1 is less than root 3. But hang on, root 3 is about 1.7, so this is certainly also less than 2. And that means a sub k plus 1 is, well, it certainly can't be bigger than 2. It's less or equal to 2. And that means the statement is true then for k plus 1, and so it's true for all n bigger or equal to 1 by induction. So, putting all that together, we now have a sequence which is increasing, and it's got a brick wall. It's bounded above by 2, and so by the monotone convergence theorem, this sequence approaches something. It's got some limit, which I'll call alpha. And once again, I take limits through the recurrence. So the limit a sub n plus 1 is the limit of root an plus 1. Now comes the surprise, because this is then going to be alpha. This will be root alpha plus 1. So I'm going to square both sides. I get alpha squared as alpha plus 1. So I get a quadratic. I can take all the terms onto this side. And now I just use the quadratic formula. It's minus b plus or minus, well, it's got to be plus, the square root of b squared minus 4ac. That gives me 5 over 2a. You can't be minus in here because that would be negative, and we know all the terms are positive by the way we've constructed them. And if you've come across this number before, this is called the golden ratio. It's a beautiful number in mathematics. If you haven't come across it before, you might like to Google that one, the golden ratio. There's lots and lots and lots of interesting stuff about this, and it just turns up magically when we look at this particular recurrence here, where we start with 1, we add 1, push the square root button, add 1, push the square root button, and so on. In the limit, this sequence is getting closer and closer to 1 plus root 5 on 2. This is a lovely example. And again, you might like to work through this carefully, make sure you can follow all the steps. You may need to revise your induction if you haven't used it for a while, but that's an important mathematical tool that we will be using in this chapter and elsewhere. Okay, final example here, which I'm just going to do fairly quickly. You can perhaps have a look at the details yourself here. So we're going to consider this sequence. It's an is 1 plus, so it's 2 plus 1 on 2 factorial plus 1 on 3 factorial plus 1 on 4 factorial up to 1 on n factorial. This again is, we'll look at series a bit later on, but I'm just thinking of this at the moment as a sequence. It's given in terms of a sum here. Well, it's clearly increasing because every time I go from an to an plus 1, I'm going to add a bit more on. So the terms are clearly getting bigger since we're adding on a positive term at each step. Now I've got to get it bounded above, and the way I do that is, you might like to check this carefully, this is 2 factorial is a half. Now the next term is 1 on 3 factorial. Now 1 on 3 factorial is 1 on 3 times 2, which is 6. And 3 is bigger than 2, so in the denominator this is going to be less than 3 times 2 times that, which is 1/4, or 1 on 2 squared if you like. 1 on 4 factorial is 1 on 4 b3 b2, and this is less than 1 on 2 b2 b2, which is 1 on 8, which is 1 on 2 cubed. So you can see what's happening here. 1 over n factorial is going to be less than 1 over 2 to the n minus 1. And so I'm going to replace 1 over 3 factorial is less than 1 on 2 squared, 1 on 4 factorial is less than 1 on 3 squared, and 1 on n factorial, same argument, is less than 1 on 2 to the n minus 1. Just pattern match between the two. And the point is that this in here is a geometric series. Now I've skipped the calculations here, but if we take a half plus 1 on 2 squared plus 1 on 2 to the n minus 1, we use our sum of a geometric series formula, which I hope you remember. I'll put it over here. It's a into 1 minus r to the n on 1 minus r from high school. So this is a half into 1 minus a half to the n on 1 minus a half. And that gives me 1 minus 1 over 2 to the n. So in fact that should be 2 to the n here, not 2 to the n minus 1. How many, oh no, hang on just a minute, how many terms are there? Oh no, I was correct, I'm sorry. There are n minus 1 terms. There are n minus 1 terms in this series. So you do get an n minus 1 there. So 1 minus a half cancels, you get 1 minus 1 on 2 to the n minus 1. And you add that one to, and you get a 3. So this is 3 minus something, and that's less than 3. You can check the details of this one yourself. So this turns out to be less than 3. So that tells me we have a sequence now which is monotonic increasing. There's a brick wall at 3, so it's bounded above by 3. And so by the monotone convergence theorem, this has a limit. Now what is the limit in this case? Well, you may possibly have seen this one before and be aware that the limit of this sequence here is in fact our old friend E again. And we will look at this a little bit later on when we look at series problems in a later chapter. So have a go through there, see if you can follow the steps that we've done there. Sorry about the little error there, which the notes were correct because there are only n minus 1 terms there. And that's the end of chapter 2.